Today is a little bit of a romp, I think. It's getting late in the semester. Not really, not even halfway through yet. And we've been talking about the kind of technical side of geothermal energy, of course. It's an engineering class. So we finished off last week talking about the chemistry of geothermal fluids. And so we've talked about thermodynamics, phase changes in being able to drive liquid to vapor and being able to use that as a workhorse to be able to extract work from a system. We've talked about subsurface fluid flow in terms of being able to recover those fluids within the reservoir and what their heat transfer characteristics are, broadly written within the reservoir, and how we can maybe sustainably recover them, how we can evaluate what the throughput would be, the yield of a reservoir would be, in terms of not so much temperature, but mainly in terms of flow rates, from understanding a bit about Darcy's law, but also in terms of temperatures and understanding that reservoirs which are re-injected and are therefore cooled and quenched can be negatively affected, so that they're chilled, so that the fluids you recover are cold if you're not careful about it. We talked last week about concepts of geochemistry and dissolution and precipitation of chemicals and what that means both in terms of the reservoir, retrograde and prograde reactions, understanding what magnitudes of dissolution and precipitation can be, and also in understanding what the difference is in retrograde and prograde reactions. And so that's kind of the nuts and bolts of how these systems work. And so from now on, we'll perhaps stand back and talk about the bigger picture, how that fits into the bigger scheme of things. So today is week 7, and up to now we'll talk about really the appraisal, if you like, of geothermal reservoirs. And we will talk mainly about the appraisal of what I would call exciting geothermal reservoirs. So the reality is that as geothermal energy gets more prevalent, then the systems that will probably make a difference, if it's baseload, it'll be things like EGS, which you can drill underneath our feet here. And if it's ground-sourced heat pumps, then those are pretty much cookie-cutter solutions. Pretty much anywhere you want to put one in, as long as you have some soil, or if you have rock, you have a different way of putting them in, you drill holes. But if you have soil, you excavate some trenches, you put in the heat transfer elements, and you're almost guaranteed to get a yield from that can work. And so those are well-engineered systems. What aren't so well understood, and which are probably largely developed out, are those hydrothermal systems that sit in very specific geological habits. And so today I thought we will talk from this week onwards for the next 4 sessions about the geological habit of those systems. We've talked about that already, but we'll look at some pictures and visit some places. On Thursday we'll talk about geophysics to prospect for those systems. And the following week, either in person or not, we'll talk about then drilling and recovery and completions to be able to finish off the recovery from those reservoirs. So the next 2 weeks is kind of that. So we're at topic number 7, and the material is taken broadly from Glassley and also from Grant, but it's not a very detailed suite of notes that we have from there. And so I'm making up as we go along. So just to get us in the mood, let's take a trip. This is one of our famous trips. If I can get it on the page, or at least it's a map of one of our famous trips. If I can get it on the page. So we've taken a number of these. I've mentioned before that we've gone with students to a variety of places. And if you've looked at any of the other stuff online, I know you might have been in class most of the time, but if you looked at the other stuff online, I think we talked about one in the UK and Iceland, and I think I zoomed through the movie last week just to give you a feeling for us. But this was one of our trips to New Zealand. This is 2013 in May, which is their beginning of their fall, I guess. Arriving in Auckland, we'll go through some pictures just to kind of to their single thermal power plant at Huntly, which is a gigawatt plant, which provides all the electricity they use that isn't provided either by geothermal or by hydroelectric power. We go to a surface paradise at a place called Raglan, where there's a wind farm with a bunch of probably 20 or 30 wind turbines, about 3 megawatt capacity each, all generating from the vigorous winds that come off the Tasman Sea. We go to a place called Arapuni Dam, a hydroelectric dam. So the Lake Taupo here is in the center of the volcanic region of New Zealand. It's a large volcanic lake. The lake runs along the Waikato River, which basically follows this blue roadway pathway here, almost to Auckland, but I think it kicks out into the Tasman Sea before that. And every square inch of this river is dammed. There are probably 15 dams along this. They're all stepped. So the first one gets the first drop, the next one the next drop. And so all the water that comes out of Lake Taupo, which is released from a gate actually in the lake, is sent along here and ultimately generates electricity before it goes into the sea. New Plymouth, they have oil and gas offshore. They have a gas field which is offshore, which comes onshore just south of New Plymouth, the Maui field, so-called. They have a Methanex plant to convert natural gas to methanol as a liquid fuel, room temperature liquid fuel here. And the South Island has no geothermal energy in it. All the geothermal energy in the North Island is physically in the Taupo volcanic zone, which is along here. And the South Island is famous and contentious at some degree because it's much more mountainous, the New Zealand Alps. Many of the rivers are dammed, and it's a large source of hydroelectric power, which is then gathered in the south part of the South Island and then sent by underwater DC cable onto the North Island for the main population centres which exist in Auckland. And so I'm trying to think where we went here. We went Westport, so there's a town called Greymouth where they had a big coal mining disaster 20 or 30 years ago. The Huntly Power Station used to burn coal. There's a coal field right around it. Now burns gas when it's turned on, is mostly being phased out. But actually last time we were there, which would have been 2019, they had actually ramped it back up again because there was a drought in the South Island, and therefore with the drought there was no electric power, and therefore they had to rely on their backup power from that. So that's kind of describing what I'm now going to show you. Well, it's dangerous to show your personal library of photographs. You never know what you might come across. But this is Huntly Power Station. You see these 4 individual components are really combustion chambers with boilers attached to them. It was coal-fired. The coal is gathered from a coal field that exists exactly around the plant itself. Now there's an add-on natural gas turbine, maybe a megawatt, maybe 300 megawatts in capacity, which is what they're using. They've ramped down the coal sides of things. So a normal power station, so something of the order of a gigawatt, a typical power station, and a control room. And Jonathan Matthews with visitor on his back, as you might imagine. The generator hall. So you saw those 4 outlines of those 4 combustion chambers. The combustion chambers produce steam, which go through these individual turbines and generators attached to those turbines. 4 units in this particular case in kind of a generator hall, all lined up parallel to this along the hall. And 1 new acquisition, which is a natural gas turbine. And so this is the turbine on this end, the natural gas goes into, and then this is the generator that puts the electricity out of it. All the accoutrements of a normal coal-fired power plant, conveyor belts to get coal into the system. Taupo, I'm trying to work out the name of this. Taupo is the name of the wind farm. You can see one of the turbines up on the crest of the mountain there, just traveling there. We stayed in a place called Soulscape that has these old railroad cars as bedrooms. It's like a hostel of kinds. It's kind of a cool place. And then I don't know how many of these they have. These are order of magnitude 3 megawatt capacity turbines. They maybe have 20 of them. It's on a quite exposed hillside, so it gets good wind lots of the time. The Arapuni Dam is one of the dams coming out on the Waikato River that comes out of Lake Taupo, and this is one of them. Apparently under some distress and is leaking, as North Island, New Zealand and South Island, New Zealand are both in pretty heavily volcanic zones, sitting on plate boundaries. A bridge to get across to it. So this particular dam, the river would come in from the left downstream. Actually, it's dammed. The dam you just saw is to the left in this figure, upstream. It takes all the water and it shunts it into a canal, which is back here. And then once shunted in the canal, it comes through the back of this scarp into the transformer hole, where it's generated into electricity and then discharged into the original riverbed and then cast downstream to the next dam, which collects it. A defunct turbine. So in terms of the geography of this, you saw those. We go back to this. So those places we just looked at were Raglan on the coast, Huntley for the power station. The Waikato River goes down this way, almost to Auckland. Lake Taupo, this whole region that's kind of delineated by a couple of parallel lines that go this direction and this direction, is a pull-apart region, which is a rift zone, which is the Taupo volcanic zone, of which Lake Taupo is part. This had a number of big historical eruptions on it. You can't see it here, but certainly in your lifetime, you might have remember a tour group on a volcanic island, White Island, which I think is probably this, maybe killed 10 people by an eruption maybe 5 years ago now, with a cruise ship tour ending up at this particular spot and being badly timed, unfortunately timed. But in this volcanic zone, this is one of the geothermal fields. This is Rotocover, I think. This is a cooling tower, so this is a condenser. Cool air being driven through these fans, which are in these cowls here. Water being supplied to them inside a radiator, so that this cooling is able to condense the water and allow it to be ultimately re-injected. Normal pipes on the site look very thick, but maybe 2/3 of their diameter is insulation, and only the central portion is the water carrying pipe itself. This may be the largest geothermal turbine in the world. I think it's something like 135 megawatts. That's Jonathan as well on the right-hand side, the control room. And kind of a topic of what we're discussing today is exploration. And so if you think about finding a site that you might want to develop into a reservoir, then you'd like to be able to de-risk it. So you don't want to put a lot of money into it until you know it can be successful. So the first things that you might want to do are the things that we'll talk about today, and that is realize the different environments that they live. And if there's a geothermal field next door to you, you might be reasonably confident that you can spend some money drilling some holes and have a viable field there. Not quite the story, but that's kind of the idea. And so once you get the right location of it, in the Taupo volcanic zone, for instance, you might want to do geophysics to be able to see what's underground. Once you confirm what you think is underground, you might want to drill into it. both to confirm the geophysics, but also to be able to see if there really is any hot water there and what that hot water might yield. And then you might want to develop it. So this just happens to be a drill rig, a geothermal drill rig. This is the mast. The drill pipe goes into the mast. This is a carousel. In each of these cassettes, there's a piece of drill pipe. Steel may be 20 feet long, I'm guessing, maybe 6 meters, which would be 20 feet, and maybe a few inches in diameter, which connects to a drill bit, which goes down the hole, and is just pulled out of these individual cassettes, raised up into the mast, and then pushed down and then drilled. We'll talk about that in due course. And so this is the drill rig, comes in on a multi-wheel trailer, lift off the ground. The mast is raised, and then all the other accoutrements that go with it. Blowout preventer. So drilling through here into something that's anchored to the ground, with the idea that the hot geothermal fluids that can flash to steam and basically explode are contained by the pressure that's applied here. I guess with these stacks you can also shear off the drill pipe. That's what they didn't do, obviously, with the Deep Horizon disaster in the Gulf in about 2010, was they had a seabed malfunction. They had a blowout preventer on it, which allows you to be able to shear off the drill stem and seal the unit so that nothing comes out of the hole. They went beyond that, and that whole unit on the seabed was destroyed and was non-functional, hence the disaster in the Gulf. A second wind farm in a different location near not New Plymouth, Palmerston North was the name of the town. Inside it, Mount Taranaki near New Plymouth, beautiful volcanic Fuji-like cone, which is close actually to where the gas from New Zealand's only offshore gas field, natural gas field, comes onshore and ultimately is used to create methanol. Wellington, boat ride to the South Island, Southern Alps, and white wine. New Zealand's famous for Sauvignon Blanc. Happy students. On the South Island as well, it's a traditional coal mining region close to the Alpine Fault. These are the Tasman Sea is off to the left here, off to the west. People standing around. End of a busy day, I guess, a bit different from the previous picture. Christchurch had an earthquake, 7.1 earthquake, maybe before we were there, maybe in 2010. They hadn't repaired very much by the time we were there. And then again on the North Island, we looked a bit at Arapuni Dam for hydro resources. This is actually it's kind of an interesting place, Auckland, and I think that's the last one. But it's interesting because that particular hydro station, it exists down here somewhere. And so you can't see it well, but the idea is quite a clever idea. So this is a separate watershed. All the waters from this will flow into the sea at Wanganui, I guess is the name of the town down here. And so if you want to generate hydroelectric from it, then you'd have to put dams in the rivers that go along the course to the sea. So another option is, of course, if you have a watershed which gathers the waters into Lake Taupo and then take them down the Waikato River here with all the dams infrastructure put in, it might be easier to take some of the water which exists high up in the watershed, push it over the top into a different watershed, and then you can use that supply of water through the existing infrastructure that you have all downstream. So the last picture that we saw there, which was this one, was exactly that. The watershed that's going southwards is on the other side of this ridge. It's discharging the water through these tail race pipes into the turbine hole here, discharging it into here, and then right behind me, and these black swans here, is Lake Taupo. So it goes into Lake Taupo, and then it's carried downstream to the Tasman, to close to Auckland, and then offshore. And so that's that. So that's kind of a little tour of, just to lighten the mood for today. And so to get back to something, I won't go through these. There's a couple of references here. Actually, it's worthwhile. Maybe I can do this one. Will it work? Doesn't seem to want to pick it up for some reason. So there's some resources online for you. Maybe I'll just open one of them. And that is, don't need that figure much anymore. So these are linked, and actually I think you'll look at some of them anyway. There's a couple of videos worth watching. Just trying to put them all on a single sheet here. This one here, we talked about geochemistry. You can see these. This is a meeting that was held in Park City, Utah in 2013, Penrose meeting. I won't play these, but there's some tutorials in here which are an extra resource. That link that I just hit there is the link to all of them, and specific ones looking at interpreting temperature pressure measurements in wells and also geochemistry, I guess is this one, are two particular ones that relate to what we've talked about. So you may or may not be interested in looking at those, but I just mentioned those as a resource in the event that you are interested. So that's what we'll talk about today. So last time what we talked about geochemistry, we talked about dissolution precipitation, why it's important within reservoirs and within the plant. We talked about equilibrium concentrations, which decide whether precipitation or dissolution will occur within a system. We didn't talk very much about reaction rates, but we did talk about the propensity to be able to dissolve fluids or precipitate fluids both in the subsurface and within the plant on surface. So we have some background in that. So Stuart Simmons's discussion here is kind of an adjunct to that. And so what we'll move on to talking about in part 7 is just to reiterate our need for this relationship that powers the product of mass flow rates, the specific heat of the fluid that's going through it in terms of sensible heat, and the temperature drop we get from recovering fluids and discharging them at a lower temperature. And we've mentioned many times that we need at least this and this both to be high. This is always going to be some magnitude that we don't have much control over. But mass flow rates can be big or small. Temperature changes can be big or small. But we need to have absolutely both of them to be functional if we're going to get anything out of the system. So we need to be able to make, in any kinds of exploration that we do, have to make sure that both of them might be quite high. This isn't so important in cases where we are going to try and engineer it. And so EGS, Enhanced Geothermal Systems, a little bit like the closed system that we looked at for, what was its name? In Rocky Mountain House, Alberta. Can you remember the name? I can't remember the name. Can anyone remember the name? No. Endeavour. Ever from Endeavour. Evor was the name of the company who's developing this as a closed form system. Inject it, put it through pipes that are in the subsurface, a closed fluid system that you recover, and then you generate either electricity or heat from it. And of course, at small scale, in your own house, ground-sourced heat pumps. Both of these are engineered. So the heat is present at some elevation and depth within the surface below us. And so long as we don't have to make permeability that has to be successful, then an engineered system can actually work reasonably well for us. But it isn't the same as the hydrothermal systems that we're looking at. So in these systems that rely on their specific location, then what we might look at are to figure out exactly what the potential geological habit might be that would suggest that these could be successful geothermal reservoirs. And we kind of know that answer already. We've talked about plate boundaries, destructive, constructive, and hotspot volcanoes. And if we know that choice of locations, we can understand both the geology of the location. We can probe that with geophysics relatively inexpensively. We can probe it much more expensively by drilling to understand what's there. and we can probe it even more expensively by using those drill holes to be able to run tests, such as flow tests, to be able to say something about what the yield is, and then go ahead and then develop the field. So those would be three kind of logical steps. I'm not sure if it's 3 steps or 5 steps, but a logical arrangement of steps to get there. And it's based primarily on this very last figure in this slide deck, and that's this. And if you're moving from not having a geothermal site to having a developed geothermal reservoir, you start off the left-hand side. You start off with a super high risk because you don't know what's there. And by the time you are investing a significant amount of money by doing completions, you want to have that risk taken away by knowing something about the site. So this is just making a point that when you first start looking at a site, you choose the right location. You go to New Zealand, you go to Taupo, and so you at least think you're in the right site. You look perhaps at a finer level to be able to see what the very specifics of the site are that you can do just by walking around. You might want to drill to be able to make sure that at 3 kilometers you have something that you can use. If you find that you have hot fluids at depth and they flow quite freely, you might want to do a well test by pumping it out to see what rate fluids come out to be able to make sure that you can get your flow rate magnitudes you want. And then if you're relatively sure of this, maybe you go and invest the rest of the money into it. And the amounts of money that you're investing aren't particularly small. $10 million for a well, perhaps. Again, for multiple wells to be able to develop the site. And so pretty soon you're talking about real money in developing these sites. And so you want to be sure that when you start spending big bucks and putting plant on the ground above it, that you actually have a prospect that is going to actually pay you back over the 30-year lifetime of it. And so the kinds of things that we'll talk about today are kind of the overview of these different geological habits. We know that they occur on plate boundaries, but I guess there are more specific things that we can think about rather than plate boundaries. And the kinds of things that you'd expect to have available to you would be geological survey reports to identify what the geology is there, some notation of what features exist, for instance, flowing springs and hot springs would tell you something about fluids that are close to the surface. Sampling waters from those fluids would say something about the geochemistry and where those fluids might come from and what their temperatures might be at depth. You can do very fancy things with the geochemistry to determine the geothermometry of the region. And from using Google Maps, but also specifically imagery at different wave bands, infrared to detect heat anomalies, and through a variety of different wave bands to be able to see exactly what is present from satellite sensing. The site may have been drilled already historically, so there may be records already available. They may be proprietary because they might have been owned by someone else who doesn't want to give it to you. And so once you've gone through this initial evaluation, then if you still think you have a prospect, then you can do the kinds of things that we'll talk about in subsequent sessions, Thursday onwards. Look at the geophysics to be able to understand what's in the subsurface, looking at methods of drilling and understanding how that happens, and then doing some well testing, putting some wells in place, and then recovering fluids from them, being able to say what the geochemical signatures are of those fluids, but also being able to measure the temperatures and being able to measure the sustainable flow rates that you might get from pumping water out of the system. And I think in week 5 we talked about well completions. Actually, I think it was the week that I wasn't here, that it was online. We talked about well test analysis. So anyway, so this comes from Glassey's book. It's really just an identification of a variety of different geological environments. This really is for hydrothermal. Reservoirs. We've made the point that EGS and ground-sourced heat pumps are pretty much engineered systems, and we know that it's going to be warm in the crust wherever we are. And so whether we're 10 feet down trying to get 55 Fahrenheit temperatures, or if we're 4 kilometers and trying to get 150 to 250 degrees centigrade temperatures, we know we can probably get those with some assurity, but we don't know whether we have permeability, and that's the engineering part of this, and we don't need permeability for ground-sourced heat pumps. So hydrothermal resources rely on high temperatures at relatively shallow depths. They could be deep depths, but they really rely on large volumetric flow rates. And this allows us to be able to get the m dot out of our system that we want. And so this classifies them. I'm not sure these classifications really matter, but these classifications A through F are shown here on this little schematic. And so this is a schematic across a plate boundary. I suppose a typical plate boundary might be one like New Zealand is not that atypical. And so if you had a section that went across this, this is the South Island of New Zealand, this is the North Island there, if you have these notes. And this is the South Island here, this is the North Island. This is a plate boundary. So one plate moving here at 7.4 centimeters a year, one plate here moving northwards at 5.1. These are the relative plate motions at this boundary. So if this plate is going 6.5 in this direction and 3.2 in this direction, then the closing rate is probably 3 centimeters per year. This is where Tonga is, I guess, right? The big eruption, the tsunami we had maybe 2 months ago, was up here on the same plate boundary, just further north. And so this is a plate that's diving underneath this particular location. So in plan view, in cross-section view, this is the incoming plate, this is the other plate. It's scraping off sediments that are deposited here as it goes underneath. These pile up. These might make coastal mountains that might come above water. The plate melts. Actually, the plate doesn't melt. The plate comes here with sediments that have water in it. There's water that's present within the minerals, kind of bound in the clay minerals. And there's also water that's present within the slab. The water rises when you add it to existing crust. If you add water to crust, you reduce the melting point of the crust. The crust melts and it makes a magma chamber, and that stuff buoys up because it's less dense than the rock around it. And on occasion, it comes to the surface, and depending on the kind of volcano, it either explodes with lots of gas inside it, or it extrudes like the Hawaiian volcanoes as a lava stream. So both explosive and effusive volcanoes. There are constructive plate boundaries where the mid-ocean ridges, such as the Atlantic mid-ocean ridge, upwelling of melt, two plates being pulled apart. The melt doesn't so much contribute to pushing them apart, but upwells in the gap that's made. So this would be somewhere like Iceland, would be a case in point, which we'll look at. This would be a case like New Zealand. This would be a case like the geysers in California. This would also be like, we'll talk about Montserrat in the Caribbean. And we'll look at some pictures of these, just by way of finding our way around. And I guess you could also have a hot stop, extensional regions in the crust where things are being pulled apart. So we talked about graben, which would flow if you pull this crust apart. Then the natural breakage of that is that you generate faults, and these faults allow a block to drop down. So instead of being at this level, it drops down to being here as you make more space for this. And this would be salts, for instance, which is an EGS site. So we'll just look at each of these geologic habits. So the main point is, if you want to be able to look at productive hydrothermal reservoirs, There are only a certain number of geological habits that they can come from, and they're related to, one, having high temperatures relatively high in the crust, in this case by melting magmas that rise up into the crust. But also, if we remember that we want to be able to get power out of these, which is given by this very straightforward expression here, temperatures, we can probably guarantee that we have high temperatures quite high within the crust at each of these locations, just because the crust is thin relative to the mantle. But we can't necessarily be guaranteed that we'll have high flow rates. So the one thing that these locations have going for them is that they are places where lots of deformation is going on. Crust is getting pulled apart, crust is getting jammed underneath, and you get lots of fractures formed. And those fractures allow fluids to be able to travel quite quickly. And the fact that it's continuously deforming, it means that the chemistry, the precipitates in those, don't completely seal them up because they're continuously deforming. And so that's kind of the issue for hydrothermal regions. And so we'll go on a little world tour with some of these places. And the pictures being initially shown here. So if we take the first of these, I don't think the classifications A through F really matter, but just to give you an appreciation of what these are. So could be the west coast of the US. It happens to be the northern part of the west coast, so it's the Cascade volcanoes. A subducting plate going underneath the Pacific plate going underneath the North American plate. Seattle would be up here, happens to be a high seismic risk zone. Portland would be here. Vancouver would be up here. Down here would be, keep on coming, would be San Francisco on this part. You have a coastal mountain range, which is from these bulldozed sediments that get pushed up by this plate going underneath. You get new plate made, which is causing this to be able to migrate under the existing static North American continent. And you get the Cascade volcanoes. Mount St. Helens is one of these, Mount Hood, Mount Baker. This whole line of volcanoes comes from the fact that the water that gets dragged underneath comes off the plate. It wells up into the crust, it melts the crust, and it's that melted crust due to the lowering of the melting point of the in situ crust that causes the magma to upwell. And so in some places it upwells as individual volcanoes. In some places it upwells as calderas. And so caldera would just be a very big blob of magma. So instead of maybe being a couple of kilometers across in size, it might be something like 20 kilometers across, just that a much larger volume is accumulated. And so the closest caldera to this would be, I guess, Yellowstone. On the east side of this plate would be a hotspot volcano existing under a plume that just makes it hot. Crater Lake is a former caldera that exploded in geological time in Oregon. And I guess this is a cross-section through the Sierra. This is Mammoth Mountain. So Mammoth Mountain is north of LA. So if you go out of LA along the back of the Sierra, so this would be the Sierras. This would be Yosemite somewhere along here. This would be Death Valley over here. This would be the basin that's included in there. And there was some worry at some stage that the Long Valley caldera, which is a big blob of molten magma, which exists in the east of the Sierra, was something that was going to cause an eruption, a big eruption. And so these kinds of places are the ones that we'll talk about. So I'm going to go back to my stuff, not that, go back to this. Did this last year to pull it up. So let's look at some pictures. So if we orient ourselves, I guess I can move between, I don't want this one. Just move between these. So if we orient ourselves, so we mentioned out of these different components, the geysers. The geysers are about 100 kilometers north of San Francisco. They exist just on the east, in the coastal mountains, which would be the same as these mountains here, and is the largest geothermal field in the world. So what it looks like is this. This was 2000. This is 2000, I guess. A young semi-esser right there. And so merely all you see on a geothermal site is a whole bunch of wells tapping the fluid from the subsurface and taking it along to a plant. These large pipes are just mainly insulation with small internal pipes inside them. I think in here these trees were killed from a release of boron gas from the geothermal fluids, as I recall. This is a condenser, the same as we saw in Taupo in the previous slides. You push cold air up through these with little propellers in them. You have water circulated in a piping system, just like a radiator in a car with lots of surface area, so that the relatively cool air, probably 30 or 20 degrees centigrade in California, cools down the hot waters and allows you to be able to re-inject it. And so it's a wooded area. This is a power plant. This is a condenser that sits on top of it. The water is being gathered from drill holes all over the many square kilometers of the site and being fed into the turbine plant. The hot fluids that come out of this being condensed and then being sent through the piping system to be re-injected to keep the geothermal reservoir full of fluid, so that those colder fluids can warm up over time and then be recovered in due course in kind of this closed system arrangement. This is just a hot spring or a seam steep that's on site. So there's definitely a manifestation of this. This is how it would have been discovered in the first place, by seeing the hot springs on the surface. And I think the same view of the condenser plant from down below. Close to Napa Valley, and so plagued with wildfires recently, but still operational. And so yeah, this is expansion chamber. This is hot water going in, steam in the larger volume manifold going out after it's gone through a turbine. And so you just see these. So the geysers on the coast. We talked about Yellowstone. Yellowstone is inside of the coastal range. And so there was maybe 10 years ago, 15 years ago, Newbury Mountain Geothermal Demonstration Project was an EGS project on Newbury Mountain, which is one of the defunct near dormant Cascade volcanoes. But Yellowstone, which is on the east side of those volcanoes, is a caldera that is almost ready to blow. It has, I think, a 500,000 year return period, and it's up to 500,000 years now. And so this is the manifestation of things there. And actually, I don't know. So Cascade volcanoes we talked about. Newbury we haven't talked about. We will talk about Montserrat, but let's not talk about that right now. I just see that the next figure that came up is the Valles caldera. And so the Valles caldera is the home of the Los Alamos EGS site, maybe in 1974. I think it's on, I think I do have it. This picture was definitely taken before iPhones were used, so it's been geo-referenced by me. Yeah, so it's in Los Alamos. So Los Alamos, if I can get that down, is in southern New Mexico, if you know the geology of the West, just north of Albuquerque, I guess northern New Mexico, near Santa Fe, which is an artist community, and the Valles caldera. There's a big caldera, just like Yellowstone, And you guys would know where Yellowstone is. It's on the Tetons, right? Where's Yellowstone? Up here somewhere? Idaho Falls. Next to the Tetons, right? So close to Jackson, Wyoming. Yeah, it's here. It's here, I think. Yes, yeah, there it is. So Yellowstone is here. So this is a caldera that sits here. Newberry Mountain is in Oregon, so it sits in the Cascade Volcanoes, which is here. The geysers is, this is Cape Mendocino. Geysers is right here, near Santa Rosa. And so those are the places that we've looked at so far. And I guess, does this take me back to the photos? It does. So Fenton Hill, the former hot dry rock geothermal site. This was 1987, 89. Already it's been abandoned by then. The wells have been taken off site. The coolers that were used to cool the fluids that were taken out, it was never a production facility, but hot fluids were cooled before being re-injected. Wellheads present on site, drilling towers on site. The data acquisition system looking very ancient these days with strip recorders. One of the wellheads going down to the wells, which probably went down a couple of kilometers with the appropriate plumbing. A cooler on the surface, fans to be able to cool fluids, and again, wellheads present on site. The other location that we talked about was Montserrat. I don't know. So Montserrat is a volcano that sits in the Caribbean. And so in terms of where that would sit, this would sit, it's fed by the North American plate going under the Caribbean plate. Water coming off and creating an arc of islands, which are the Caribbean islands. And so if you look at the mechanism by which that works, I don't know if I have this here. I think I have a map of it. Okay, right on. So just to get your orientation. So this is Puerto Rico. This curved arc is the plate boundary. You have the North American plate diving underneath the Caribbean plate, making this arc. And all the islands that are on the inner side of this are all volcanic islands. And all the islands like Aruba, which is sitting here, are islands which are the scraped off sediments on the outside edge of that. So Antigua is mainly a limestone island, a reef island. All of these are individual volcanic centers, which are producing either dormant or producing. So Montserrat began erupting in 1995 and took a, actually I don't know if I have, I should go back to look. I don't think I have any pictures of that here. See what comes up for this. Should look at images. They must have some of these iconic images. So this was what Plymouth looked like in 1995. It was a beautiful, pristine island. I guess I won't play that. But if you look at this clock tower, didn't quite open. Yeah, okay. Well, I guess I can go to my pictures for the death and destruction part. And so if you look at what was a functioning city, the population of the island was something like 10 million. I think in 1998, not 10 million, 10,000. 7,000 of those inhabitants left to go to London because there's an exclusion zone. This is the same clock tower that you saw previously. This would be 2002, as I recall. So it was 5 years later than that. And this is the former town of Plymouth, which was the capital city of this island. And we had a scientific drilling program there to try and understand exactly how the volcano was operating, which involved drilling a bunch of holes. Closest one maybe 5 kilometers away from the volcano. And these holes had very sensitive instrumentation in, put at 200 meters depth, to be able to measure the strains in the volcano. And the strains in the volcano change depending on whether fluid's coming out of the top of the volcano or whether it's accumulating in the magma chamber. And so if you look in the subsurface and look at monitoring the changes in deformation in the subsurface, you can say something about the accumulation of fluids within and understand exactly the mechanisms by which volcanic eruptions are triggered. I had my cursor on it, but I didn't point to it. The island south of Montserrat is Martinique. They had a eruption in 1902. They had the 100th anniversary in 2002, which killed, 10,000 people. It was a nuée ardente, which went through the main city of the town. And the story is that the one guy who was drunk and was put in jail, his name was Cyprius, I think, was the one guy who survived the nuée ardente because he was in the jail and kept out of the cloud of hot gases, which basically killed the whole town's population. And so if we look at the geometry of that, that's an island off to the south. So I don't need that. Where was I with this? All right. So if we go through these, we've been through Soufriere Hills. That's the Soufriere Hills volcano. The town of Plymouth is right under the plume at this side here, as it turns out. It's misoriented. This is north in this direction. The geysers we've seen, and the other one we talked about was Schwartz. And so if you look at places where you have sedimentary cover, and you have parts of the crust being pulled apart. One such place is on the border between Germany and France, the Rhine River Valley, where this would be Germany on this side, this would be France on this side, pulled apart. You get these graben being created, and this is the site of the European Hot Dry Rock Project, or the EGS project, which are a series of wells which have been there since the mid-1900s, which are plumbed down to 5 kilometers of depth. They are wells in which fluid is injected in some of them, you see by the blue arrows, and recovered from one of them up to the surface. It's not creating any electricity of any consequence, but it's an experimental site to be able to evaluate the feasibility of such a concept of being able to drill to 5 kilometers initially in favorable conditions where the geothermal gradients are high and in a Rhine graben deformations that are occurring all the time keep the porosity open and the permeability open, but then to be able to migrate it to other places such as underneath our feet. And with many of these things you can't see much what's going on. This is Schwartz. This is what it looks like. This is one of the former wellheads, and there's really nothing much to see on site there. Mount Shasta, one of the Cascade volcanoes that's further south. Mount St. Helens, which is one of the Cascade volcanoes which erupted on May the 18th, 1980, and what it looks like now. This was a Fuji-style volcano. The whole west side of this blew off in a lateral blast in May of 1980 and left this blew down all the forest that was on there. And I think the remnants of that was taken in 1982, I think. And finally, out of these, as we go through all these different ones, Taupo. And so we've made some suggestions about our travel here. So this is Auckland. This is Lake Taupo with the town of Taupo next to it. This is the Waikato River that goes down to the sea. This is the Taupo volcanic zone, the TVZ as they call it, which are two graben. I guess it would look a bit like this. So this part of the crust is being pulled apart. This is a subduction zone. The water is boiling off the subducting plate and rising. It's melting the crust, where it lowers the melting temperature of the crust by adding water. And with this melt, this exists underneath the whole region as a caldera, essentially. The caldera allows subsidence to occur and upwelling of magma into erupting volcanoes, active volcanic region. The active volcanic region runs from White Island, where we made the point that these tourists were unfortunately killed 5 years ago when they're touring the island due to an unexpected eruption. And these graben go all the way down to, actually we looked at a Fuji-like volcano, Mount, it's escaped me, but it'll come back to me, that sits here next to New Plymouth, and they're all arranged on a fault line that goes across Mount Taranaki. And actually, interestingly enough, this volcano that sits here is surrounded by an onshore oil and gas reservoir and an offshore natural gas reservoir here. And so this is the plate boundary. Plates are going underneath the island, as you see here. This is drastically exaggerated. They probably go in at 20 degrees below the vertical. And this continues on to the North Island. And the North Island, the fault is a strike-slip fault, like the San Andreas fault, which is failing laterally. This is the town of Christchurch that we saw the earthquake damage from just recently. 2017, there's a Kaikoura earthquake, a big earthquake again in New Zealand. And this is the place where all the geothermal resources are developed within New Zealand. So if we look on this, what's this? So this is exactly that. This is the Wairaki geothermal field. So it was the second active geothermal field that was exploited in the world. The first one was in Larderello in Italy, in the Apennines. Its claim to fame was that Larderello was mainly water, is present in the reservoir. This happened to be predominantly steam within the reservoir, a much hotter reservoir. And so all the technology had to be developed to be able to recover geothermal energy for this. You see that these are a whole bunch of insulated pipes that are collecting water from wellheads. Here's a wellhead that's off-gassing here, and they go all the way up the valley. They're on rollers so that they can thermally expand or contract. Where they go across roadways, you have them arched so they can also take up the thermal expansion and contraction, and you can also drive underneath them to get from one side to the other, just as a way of being able to both accommodate the thermal expansion in the pipes and also be able to have roads that go underneath these regions. You'll listen to a recorded talk by Greg Bignell, who is this guy here, who used to work at the New Zealand Geological Station, GNS. It exists at the Wairaki site, talking at the overlook, tourist overlook at this particular place. I think this is Rotocover, which is another geothermal field very close by, which is used for generating electricity. I think this is the place that has that largest geothermal turbine in the world, 134 megawatts or so. But also the excess heat from this is being used in a plant for processing wood. So New Zealand has heat at depth. It's on an active volcanic zone, and so therefore it has porosity and permeability, but it also has, where it sits, a lot of rainfall. And so because of the rainfall, it also has a lot of trees, and the lumber industry is something that is a big part of the economy of New Zealand. So treating and then drying lumber as processed chipboard or just as processed lumber uses geothermal heat to be able to do that. And I think also in New Zealand, we've never visited it, they also have places where they have hothouse tomatoes which are grown using geothermal heat. A cyclone to be able to put in water here. The water flashes to steam and goes around the cyclone. The water is decanted off, so that actually this would be the influent portion in the system. Water would come in here. It would swirl around here. It would convert to steam. The steam would be taken off as a decanted gas, and the water, as it condenses in the bottom, would be taken off as a liquid. So it gives you the option to be able to bring in a mixed fluid of both hot water and gas, separate it into components which are gas and liquid, and then do something separately with each of those streams in terms of generating electricity from them. I think this is a tank that's used for putting sulfuric acid into the water to be able to make the silica settle out so it doesn't go into the plant. And again, another picture of a condenser. Air coming out of these things that have propellers or fans inside them, water going into this and being cooled and then coming out as cooled fluid. If you look inside here, you see the condensed fluid just dripping down and then being collected and then taken off to being re-injected. That's the rainfall that we're supposed to get here later on today. And I think that is White Island. So this is taken from the TVZ, as New Zealand would call it. And this is White Island, the dormant, but not apparently dormant all the time volcano. Yeah, this is Taranaki. This is that volcano that sits in the oil and gas field. Tenerife, one of the Canary Islands. And so we didn't say anything in this class today about, oh yeah. So the other geological habit, I suppose, would be hotspot volcanoes or on constructive margins. So hotspot volcanoes would be like Hawaiian Islands. And so the idea is the hotspot exists in one place and stays there, but the plate is migrating across it at some rate, maybe a few centimeters per year. And so this single hotspot generates a volcano that stays in one place, but the plate migrates away from it. So old volcanoes that were once here are migrated away from it. Erosion occurs and they fall apart and they get smaller and smaller. So if you look down the chain, you see the large ones which are actively being produced, the smaller and smaller ones that are older and older as you get further away, and that are being destroyed by erosion and then will ultimately disappear below the waves, while new ones get created as Mauna Loa indeed migrates off-site. So hotspot volcanoes have active upwelling from a plume, and ocean ridge volcanoes, which I don't have a cross section to show. I guess the only cross section is this cross section. I guess this would be a ridge volcano. This would be Iceland, that happens to have in some places be below the ocean surface. In Iceland, it just happens to be above the Atlantic Ocean surface and therefore is useful at a geothermal site, but then acts as the ability to be able to recover it. So again, some pictures here. So this is Tenerife, I think, or La Palma, which is one of the Canary Islands off the west coast of Africa, south of Spain. I won't go to a map. You probably know where it is. This is the Azores. So the Azores are essentially right on the mid-Atlantic ridge, are a transit point between Christopher Columbus going between Europe and the New World. And this is sitting on a volcano. And this is for a meeting where they actually dig holes and they put your dinner in those holes to cook with the hot steam. So you put your stuff in there, I guess wrapped up within a big pot, encased in linen. You leave it for 2 hours to cook the seafood. You come back and retrieve it, and then you go back to your restaurant and eat it. And so this is just one of the volcanic lakes that exists there. I think this is San Miguel, which is one of the towns. That's what those domes look like while they're cooking. A pot here, a pot already underground, and then recovered and eaten. This is Iceland. So sitting exactly on the Mid-Atlantic Ridge. I'm sure you know where Iceland is. This is when we were there with students in 2003. This is just near in the Reykjanes Peninsula in the southwest of Iceland, where the Mid-Atlantic Ridge comes onshore. And it's very close to that, where a number of the geothermal plants are. So just wandering around a geothermal field. This is very close to that. This is the so-called carb fix site, where the idea is to inject into the basalt a fluid that contains water and carbon dioxide. And the idea is that the carbon dioxide gets mineralized into carbonate and geologically or mineralogically bound to the basalt by its injection. So it's one of the CO2 sequestration solutions that uses the fact that these rocks are relatively hot at relatively shallow depth. They're relatively permeable because it's being pulled apart in a constructive plate boundary. And so you can always inject it in because it always has permeability. And it's hot enough that the heat in the ground provides the energy that fixes the carbon physically to the rocks so that it's no longer present within the atmosphere. So that's the carb fix site. This is just elsewhere on the Reykjanes Peninsula, probably near Nesvellier, just the steam coming out of some of the wellheads from some distance away. This is an effluent pond, so producing the fluid from the subsurface. If you don't re-inject it all, then you're left off with some on the surface. This is just a pond as it's kept. If any of you've been there on the green program, I'm sure, or otherwise, I'm sure you'd have gone to the Blue Lagoon, which is just the same, an effluent pond that they charge you $20 to go and sit in and be regenerated by the minerals that are in the water. So they've turned their effluent ponds into a money-making prospect, which is quite clever, of course. This is Nesvellier, which is a geothermal site close by. These are the individual well heads that you see steaming. These are the pipes that collect the geothermal fluids and take it to a central geothermal plant. I think this site produces some of the hot water that's used in Reykjavik. Of course, of course, the word geyser is an Icelandic word for geyser. And so I won't make you sit for all of this, but this is just a recording of the original Atlantic geyser. Peat, another geothermal plant close by to Reykjavik, not very far away, with these tanks that are allowing fluids to expand. The generator hole inside, very clean, and I guess that's the end of my slides. And so that's kind of the big picture geological wise. So we made the point that we'd like to be able to understand something about where we might want to prospect for these. The biggest picture we can have is by understanding its kind of location in the world. This might not be the systems that we rely on if we're looking at EGS or ground surface heat pumps, but at least for deep geothermal and hydrothermal, these are the habits they come in. And as we look at trying to evaluate how to develop some of these sites, this is the figure that we kind of refer back to. And it's all about trying to be able to de-risk the the site in terms of making sure that if you're going to invest a very large amount of money, that you make sure that you are guaranteed that you have a product that is going to repay that money over the lifetime of the project. And so what we've been talking about, I suppose, would probably come in this category here, understanding at least exactly what these sites look like. And what we'll do from now is we'll talk about geophysics, which is relatively inexpensive and can give us some information. We'll talk about drilling, which can give us some information to confirm what the geophysics says to us. From then, if we drill and we find hot fluids, we can complete the wells and pump test them to make sure that they flow at a rate enough for us to have a plant. And then you start building the surface plant to be able to do that. So that's kind of the big picture item here. So we've talked about this part today. What we'll talk about next time is to talk about the geophysics that we might apply to be able to do that. So we'll be in the class today, as we were, and Thursday, and then on the week before spring break, the 2 classes that will get served to you will be asynchronous and online. Okay, that's where we're going.